It was moving too fast to belong here. When astronomers first calculated the speed of a tiny dim object passing through the inner solar system in 2017, they realized it was unbound. No orbit, no return. It was the first confirmed visitor from another star system. And then it got weirder. As it receded from the sun, it gently sped up, as if pushed by something invisible, yet showed no trace of the gas or dust that usually cause such accelerations. Its shape, its motion, its silence in every wavelength we checked. Almost nothing about it fit our expectations for a normal space rock. Astronomers named it Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first. It was discovered by the Pan-STARRS telescope on Haleakala, which scans the sky for moving objects that might threaten Earth. But this one wasn't a threat. Its path through space, a hyperbolic trajectory, told us it had fallen into the solar system from interstellar space, swung around the sun, and was already on its way out before we even noticed. For the first time, you were about to meet a piece of another planetary system, passing through our cosmic backyard. So what exactly was this thing? From the brightness alone, Oumuamua was tiny on astronomical scales, probably between 100 and 200 meters across, roughly the size of a skyscraper laid on its side. But it didn't reflect light like a sphere. As it tumbled, its brightness changed by a factor of about 10, suggesting a very elongated or flattened shape. Early estimates imagined a cigar-like body perhaps 10 times longer than it was wide. Later modeling showed it could also have been a thin, pancake-like shard. Either way, it was unlike any asteroid or comet we'd ever seen up close. Its orbit was even stranger. Most comets and asteroids in our solar system follow ellipses bound by the sun's gravity. Oumuamua's path was a hyperbola with an eccentricity of about 1.2. Just over the threshold, that means never coming back. It entered the solar system from above the plane of the planets at about 26 kilometers per second relative to the sun, dove inside Mercury's orbit, then slingshotted out, leaving it around 87 kilometers per second relative to Earth. That speed, combined with its incoming direction, didn't match any known family of long-period comets. This was not a distant Oort cloud object knocked inward. It was truly interstellar. To understand why Oumuamua is so puzzling, you need to know what we expected an interstellar visitor to look like. For decades, theorists predicted that other star systems should eject countless icy planetesimals, comet-like bodies during planet formation. These objects, wandering the galaxy for billions of years, would be dark, cold, and covered in volatile ices like water, carbon monoxide, and carbon dioxide. When such a body passed near another star, the heat should vaporize these ices, creating a coma and tail, just like our comets do when they approach the sun. And comets don't just look pretty, they behave in measurable ways. As ices sublimate, turn directly from solid to gas, the escaping jets act like tiny thrusters, giving the nucleus a non-gravitational push. We see this in almost every active comet. Their paths deviate slightly from pure Keplerian orbits. So when Oumuamua's trajectory showed a small but significant extra acceleration, decreasing with distance from the sun, the simplest explanation was comet-like outgassing. But telescopes saw no coma, no tail, no spectroscopic signature of gas. It was as if an invisible rocket engine was firing with no exhaust. The acceleration itself was subtle but real, about 1 part in 10,000 of the sun's gravitational pull at its distance. That's tiny, but with precise tracking over weeks, it added up. The team led by Marco Micheli analyzed its motion and found that a purely gravitational model failed. Only by adding a radial, sun-directed force that dropped off roughly as the inverse square of distance could they match the data. That pattern is exactly what you'd expect from something driven by solar radiation or heat, not by random jets. Yet Oumuamua's surface area seemed too small and its reflectivity too low for sunlight pressure alone to do the job, unless its density or geometry were very unusual. This is where the hypotheses multiply. One idea is that Oumuamua was extremely thin and low density, like a cosmic sheet of aerogel or a fractured crust of volatile rich ice. In that case, solar radiation pressure, the momentum carried by photons, could noticeably push it, the way sunlight pushes on a solar sail. Another model suggests it was made largely of molecular hydrogen ice, Hydrogen sublimates invisibly and efficiently, providing thrust without leaving a detectable coma. But hydrogen ice is fragile. Could it survive the harsh radiation of interstellar space for hundreds of millions of years? Many physicists doubt it. A more conservative explanation is that it was a fragment of a larger body, maybe torn apart by tidal forces near its home star. Imagine a Pluto-like world getting too close to a giant planet, shredded into elongated shards. Over time, cosmic rays darken the surface, forming a rigid crust that traps most volatiles inside. When such a shard passes near a star, only small amounts of gas escape through cracks, producing enough thrust to alter its orbit, but not enough to form a visible coma. In this view, Oumuamua is exotic, but still natural, a new class of dark comet we're only now learning to recognize. And then there's the idea that grabbed headlines. What if it was artificial? A few researchers, most prominently Avi Loeb, pointed out that an extremely thin, reflective object, like a light sail, would naturally experience the kind of acceleration we observed without outgassing. Its unusual shape, lack of detectable emissions, and interstellar origin made it tempting to speculate about alien technology. The Breakthrough Listen project even pointed radio telescopes at Oumuamua, searching for narrowband signals. They found nothing. The vast majority of astronomers consider the artificial hypothesis unnecessary. Natural explanations, while weird, are more plausible. But the debate highlighted how little we know about the diversity of objects drifting between stars. Whatever its nature, Oumuamua matters because it's a physical sample, however distant, of another planetary system. Its trajectory suggests it came from the general direction of the constellation Lyra, but after millions of years of gravitational nudges, its exact birthplace is unknowable. Still, its mere existence confirms that planetary systems like ours eject solid bodies into interstellar space all the time. The galaxy is likely filled with trillions of such wanderers, silent messengers carrying clues about alien chemistry, geology, and dynamics. Oumuamua was just the first one we were lucky enough to catch in the act of passing through. And we didn't have long. By the time we realized what it was, Oumuamua was already racing away. We had only a few weeks of good observations before it became too faint for detailed study. No spacecraft could possibly catch it with current technology. The delta V required would be enormous. That urgency has inspired new mission concepts, like interstellar interceptor probes kept on standby in solar orbit, ready to launch at high speed when the next visitor is spotted. Projects like ESA's Comet Interceptor are early steps toward this idea. Flexible spacecraft designed to ambush a yet unknown target. The discovery also changed how we searched the sky. In 2019, we found a second interstellar object, 2I Borisov, which looked much more like a classic comet, complete with a bright tail and gas emissions. Two interstellar visitors, with very different properties, in just a few years suggests that such objects may be common. We just weren't looking carefully enough. The upcoming Vera C. Rubin Observatory, with its legacy survey of space and time, will scan the entire visible sky every few nights. It should detect many more interstellar interlopers, giving us statistics instead of a single tantalizing outlier. Yet the core mystery remains. What exactly was Oumuamua made of, and what carved it into that bizarre shape? Was it a hydrogen iceberg, a nitrogen shard chipped off a Pluto-like world, a porous fractal of dust and ice, or something we haven't even imagined? Why did its surface show no obvious signs of typical cometary activity, despite clear evidence of non-gravitational acceleration? Each proposed model solves some aspects of the puzzle while creating new problems. With the object now far beyond the reach of our instruments, we may never know its true composition. So the most important open question is not just what was Oumuamua, but how weird is it really? Is it an extreme outlier, a 1 in a billion freak, or the first example of a whole population of strange interstellar debris that we'll soon find everywhere we look? The answer will reshape our understanding of how planetary systems form, evolve, and shed their leftovers into the galaxy. Until the next messenger arrives, Oumuamua remains a cosmic riddle, a reminder that the universe still has surprises for us, and will be here at Terra Nova when the next one appears.